Okay, so today we are going to begin to talk about the tensor product of modules. Um, to motivate the general definition of a tensor product, we will consider the question of extending the scalars or changing the base ring um, of an R module. This is the approach that Dubit and Foote takes, and we'll follow along similar lines as they do. So to begin, we'll point out something that's pretty obvious, but we'll formalize it. Um, so we let S be a ring with unity, which will denote 1 sub S. R is a subring of S, where the unity in R is equal to the unity in S. This condition allows us to talk about or make sure that all of our R modules are unital. And we're going to let M be an S module. Now we can naturally consider M to be an R module by restricting the action of S on M to an action of R on M. Right? And this is a simple restriction because since S acts on M right through this operation S cross M um, so we know S acts on M through this operation that satisfies the module properties. We can naturally consider R acting on M because, of course, R is just a subring of S. So we have a map R cross M onto M that satisfies the same module properties. So this is a not so interesting because of course that M is an R module because R is a subring of S. By acting through S, we're automatically acting through R. So this doesn't really give you anything new, or it doesn't give any new structures or anything interesting to think about. The interesting thing is to consider the reverse case of this. So to consider if we have an R module, if R is a subring of S and we're given an R module M, is there a way to extend the action of R on M to an action of S on M? Um, so as we pointed out, this is the previous the restricting from the action of S to an action of R is called restriction of scalars. This is a very natural process to take. Um, now the question, as we said, to go in the other direction, if M was an R module, can we extend the action of R to an action of S that is compatible with the original action? Okay, so um, what does that mean exactly? Well, that means that if we somehow extend, if we have R acting on M, we want to somehow extend this so that, um, let's say, like extend to an action of the whole ring S, such that when we restrict back from the action of S, restricting it back to R, we get the original action back. So such that restricting such that restricting this new action to R, we get the original action. Now, the answer to this question is, in general, no. This does not work, and it doesn't work in even the simplest cases. Um, the case that Du Foot points out in the book, and I think this is a perfectly acceptable case, and it's the most illuminating case for a number of reasons. So we see that Z is, of course, a Z module, but we can't, and Z as a ring is contained in Q as a ring, right? So now when we say, so we know that Z is a Z module, and this Z right here is contained in this Q. So in the module, in the action, right? So the Z that's acting on Z, that's contained in the Q, in Q, in Q module. Uh, that doesn't make any sense. Uh, the Z is a Z module, of course, but we can't make it into a Q module. So we see that if we could, we would get something like this. So we'd have 1/2 acting on the element 1. That would be some, if Z could be made into a Q module, 1/2 acting on the element 1, that would be equal to some integer in Z. But then we would get Z plus Z is equal to 1/2 acting on 1 plus 1/2 acting on 1. And if this, since this is an action, we can factor out our 1 to the right, and we get 1/2 plus 1/2 acting on 1. That would be equal to 1 acting on itself, or 1 acting on 1. These are technically two different ones, right? So this one is in Q. That's the unity of Q. And this one is the unity of Z. Um, but this action, since we're assuming that this is a Q module, this would just give us 1 again. But that shows that the sum of two integers is equal to 1, which is so the sum of two of the same integers is equal to 1, which of course is impossible. So this shows that in general, we can't extend Z, the action of Z on Z, to an action of Q on Z. But we do notice that there are a couple of niceties that we can pick out from here. As I've written, not all is lost though. While Z couldn't be made into a Q module, the Z module Z is contained in the Q module Q. So what does that mean? That means that there's some homomorphism that takes our Z module Z and maps it into our Q module Q. Now when we're in, this isn't saying that Z is a Q module, but this is saying that the structure of our Z module is somehow embedded in the structure of a larger module, a Q module Q. Whereas if we restrict the action, right? So if we go in the opposite direction and we start with our Q module Q and we restrict the action of Q, we can restrict it to an action of Z on itself. Um, and so this motivates the question as to whether instead of trying to extend the action of an R module, the action of R on to an action of S, can we map our R module M into some S module such that M is an R submodule, right? And that's exactly what we're seeing with our example with Z as a Z module, right? We have Z as a Z module. We can map it into a Q module, which is Q, and Z lives inside of our Q module as a Z submodule. And this is actually the nicest case because this is actually an embedding. This is an injection, right? So like no information is lost when we embed or when we map our R module into our, or when we map our Z module Z into our Q module Q. No information is lost there. Um, in general, this map is usually not an embedding, so it's just some kind of homomorphism. Um, so we're going to proceed to construct an S module, which is the best possible target to map our R module M into. And by best possible target, what we really mean is that it's going to satisfy some universal property that we're not going to cover in this video. But the universal property has to do with maps from, we start out with our R module M, and we have a canonical map into our what we will show to be our tensor product, which is an S module, um, and then all other maps from M into um, S modules will factor uniquely through um, our canonical map. Um, but we'll save that for another video. So to begin this construction, let's examine the properties that an S module needs to have, right? So if M, so we're starting with an R module M, and R is a subring of S, what would we need in order to um, make M into an S module, or create some kind of S module that contains M, right? Now to start, of course, we need a map from S cross M into M, right? So this would be the action of S on M, um, where we denote the pair S comma M in M by Sm. Now to construct an S module that homomorphically contains M, it's natural to consider the free abelian group, so that's the free Z module on the set S cross M. Um, we'll see why it's natural to consider this in a moment, but there really is no other way to construct this because we need an abelian group for S to act on, and we need an abelian group for S to act on that contains M in some fashion. Maybe not as an injection, but contains M. Well, the free abelian group will contain the product S cross M, um, and we want it to contain M in some fashion in the end when we're done with the construction. So this is actually the most intuitive group to consider. So we'll denote the free Z module on S cross M as FA of S cross M. So that's just for free abelian and parentheses S cross M. Um, Now we recall that the free abelian group on S cross M can be thought of as the set of all formal commuting sums of elements of the form S comma N, S comma M for S in S, and M in M. So for example, an element in the free abelian group on S cross M would be something like 5 SM plus 2 S prime M prime plus S double prime M double prime. So it's just any kind of finite commuting sums of this form, with of course S prime, S double prime, S, M, M prime, M double prime in M. Now there are other ways of looking at this, right? So the traditional way to look at this would be to look at all functions. Um, would be to look at all functions f map M cross n, oops, that map S cross M into Z such that f has finite support, then we can identify um, and then we can identify the the elements of S cross M as the functions that take on, so the functions f S comma M of x, which will be equal to 1, or this should be x comma y, 1 if x comma y is equal to S comma M, and 0 otherwise. So this is the traditional way to look at these, to look at them as functions of finite support. And this injection, this this is an injection from S cross M into this new structure, this space of functions. And this space of functions can be given group structure, because it inherits its group structure by pointwise addition. Um, it inherits its group structure from pointwise addition in Z, and it becomes well, that would just be, since it's a free Z module, so it's an abelian group, and it's a Z module from the Z module structure in Z itself. Um, but this is going to be the most useful notation that we'll use, this finite commuting sums of pairs of elements. So now we want the free abelian group on S cross M. So we have an abelian group. We want it to have S module structure that's compatible with the R module structure that's already in place on M. Now, in general, so this is just back to the map, right? So S cross M, the map from S cross M into M, for this to give S module structure on M, we require the map to satisfy these axioms. And these conditions motivate what the operations that we're going to do to our pre-abelian group to ensure that we do have S module structure in the end, to ensure that we do have S module structure. Um, and so essentially what we're doing is that we're going to look at the subgroup generated by these kinds of relations, and we're going to mod out our free abelian group by this subgroup. So to ensure that we can impose S module structure on the free abelian group that's compatible with the action of R on, this should be in M. So we are going to quotient out by these relations. So we're going to let H be the subgroup generated by the following elements. So we are going to generate a subgroup of the free abelian group by these elements. And now this is going to ensure that when we do define um, uh, the module action on our tensor product on this quotient, so we're going to define module action on this quotient, that the action is well defined. This can be very important. And this last relation here ensures that the action is compatible with that of the action of R on M. So now, just a note, of course, since the free abelian group on S cross M is an abelian group, H is a normal subgroup, so we can take quotients by it. Um, and as I said, these relations ensure that the quotient will have the necessary structure in place to allow us to define action of S. And we denote the quotient, so this is where this notation comes from. We denote the quotient, so we denote this quotient, this by this symbol, this strike through this circle with the cross in the middle. So this is called S tensored with M, and the subscript R is um, to remind us what ring we're tensoring over, right? And that's to remind us about this compatibility relation. So we're tensoring over the ring R, and this is called the tensor product of S and M over R. And we denote the coset, right? So if we recall, this is just this is a this is a quotient, right? So an element in the quotient, right? So we have a canonical map from the free abelian group on S cross M onto the free abelian group on S cross M mod H, right? So it's going to send an element here, which is just of the form SM, or it's some sum of SMs, and it's going to map that to, well, it's going to map it to an element of the form. Here we could just look at it like this. It's going to send SM to the quotient SM plus H. and it's going to, since it's a homomorphism, it's going to extend linearly, so that's no problem. Um, and we denote the coset, right? So we denote the coset that contains SM. So like this coset here, we denote this by S tensored with M. We denote this by S tensored with M. So we have in our, some things to note here is that because we're working with cosets now, right? Because we're working with cosets, these tensors are represented non-uniquely. Because if we recall, there could be many representatives for cosets. Um, so a so this we have to remember that by working with this symbol, S tensored with M really represents a coset. So there's many different representatives that we can have for the same tensor. Now we have not yet defined the action of H on S tensored with M. Um, so for the time being, this is just an abelian group. Um, and in this abelian group, by the construction of H, or by the construction of the subgroup H, we have forced the following relations on the tensor product. So we have these three relations on our tensor product. And this just comes from our relations, right? So in the quotient, right? So if we recall our relations here, right? So we have this is the subgroup generated by H. So in the quotient, right, we have something like this. So S1 plus S2, comma N minus S1 N or M minus S2 M plus H, right? So this is the coset of, this is our, we take this element of H, projected into our quotient group. This is going to be this equal to 0 plus H, right? Which gives us the relation S1 plus S2, comma M is plus H, right? So this is all in here is equal to S1, comma M plus H plus S2, comma M plus H, right? So that's where that relation comes from. And then if we just translate this into this fancy tensor notation, we obtain S1 plus S2 tensored M, S1 tensored M plus S2 tensored M. Right, so we have all these nice relations um, among our elements of the quotient. Um, we can also observe that every element of the quotient can be written as a sum of these pure tensors, right? So that every element of our quotient can be written non-uniquely as a sum of these simple tensors. Now we're going to define the action of S on the tensor product, giving it S module structure. So as I said, we note that every element of the tensor product can be written non-uniquely as a sum of simple tensors of the form S tensored with M. So we're going to define the action as follows. So we're going to have S acting on some sum of, so this is just some element of our quotient. Then we're going to have the action be acting on the first component, right? So we just have this action on the first component being multiplied by the first component. And we want to show that this action is well defined. And this is where our where the relations that we quotiented out by are going to come in handy. So we want to show that the function S cross S tensored with M on that maps onto S tensored with M is independent of choice of representations of elements as this sum of simple tensors. So first what we're going to do is look at how elements of S act on elements of H. Okay, so if S prime is any element of S, then we can notice that all of these, all of these are just elements of H again, right? So when we multiply, so when we have the action, and we have S act on the left by this multiplication in the first component, um, we obtain another element um, of our group H generate, and it's another generator actually. So S acting on the generators of H by multiplying by the first component by um, multiplying the first component by, this should be a lowercase s, um, this gives another generator of H. And since elements of H are, of course, just z-linear combinations of the generators, it follows that any element, so this is just some element of H, as a sum of the generators, we can just write it this way. Um, this is going to be an element of the form, or the element s s I comma m sub I. So this sum, where we sum over these elements in the generators, these generators, is again an element of H. Okay, so this is going to be useful. Um, So this is going to be useful when we show that it's well defined, right? So now let's suppose that we have two representations of the same tensor. So we have this representation and a different representation of an element in S tensored with M. Um, then we have that their difference is equal to 0, right? This implies that their difference here is an element of H, right? Because if their if their difference is equal to 0, that means that they have to be an element of H, or their pre-images have to be an element of H. That's what I meant to say. Um, so now, by what we have shown above, we know that multiplying an element of S, um, an element of S, um, by gives us another element of H. So by acting by multiplying on the left by an element of S, we get another element of H. Right, so we get this relation here. This guy is an element of H. Now, um, we can pass back to the quotient, and in the quotient here, in the tensor product, we obtain this relation, which shows, of course, that they're equal to each other. So this shows that S sub I tensored with M sub I is equal to the sum of S sub I prime tensored with M sub I prime, which shows that the action, of course, is well defined. Um, And then we just have to check that the S module axioms are satisfied. It's enough to check this on simple tensors, since, as we recall by the definition of the product here, um, yes, by definition of our action, we define the action to be over um, the sums of simple tensors. So we can just check how the action looks on simple tensors. So on a simple tensor, we have S plus S prime acting on S sub I tensored with M sub I. That's going to be S plus S prime times S sub I. So right, so this is taking place. So this product right here is taking place inside of the ring. Um, we have distribution inside of our ring S, um, and then our third line that is comes from the um, that comes from the properties of our tensor product, and then we could just pull out our scalar by definition of the action. Again, by definition of the action, we have the sum of two simple tensors, S acting on the sum of two simple tensors. That action distributes naturally, um, by way of how we defined our action. So there really is nothing here that we need to check. And lastly, when we have 1 acting on S sub I tensored with M sub I, that's just 1 times S sub I tensored with M sub I, which is equal to S sub I tensored with M sub I. So this does indeed give us S module structure on our tensor product.